everyone, this is our ESC 220 project on solar photovoltaics by Brody Deal, Ryan Pelton, and Dawson Leach. What is photovoltaic technology? Through a broad lens, photovoltaic technology is a conversion of energy from the sun into electricity. Throughout this presentation, solar photovoltaic technology may be referred to as solar energy, solar cells, or PV cells. Solar energy currently makes up about 5% of global electricity generation, which makes it the third best source for a form of clean, renewable energy. The process of using the photons that come from the sun's rays and turning them into an electrical current is known as the photovoltaic effect. Solar cells utilize the properties of semiconductor material to guide electrons through their electrical current journey. History of photovoltaics. Something as simple as amplifying the effect of sunlight through a magnifying lens is an example of photovoltaic technology. The simple process of focusing a beam of light into a very focused region has been around for thousands of years. The utilization of this technology into society has only been seen for about 200 years. The first sign of this kind of work was seen in 1839 by a physicist in France named Edmond Becquerel. The physics and theory behind the process was studied extensively before coming out with a patent around 1888 by Edward Weston. The first large steps made in this industry were made by Bell Laboratories in 1954, when photovoltaic energy was able to power a toy Ferris wheel and a small radio. This proved itself to be useful as it was used on Vanguard 1 in 1958 to power the small radios. Using this technology enabled the satellite to transmit information for several years, which in comparison to a normal battery is much longer. It also became a crucial part of Vanguard 2, Sputnik 1 and 2, and so forth. Types of solar cells and how they work. There's monocrystalline solar panels, polycrystalline solar panels, passivated emitter and rear cell solar panels, and thin film solar panels. Monocrystalline solar panels are made from a single silicon crystal. They are more difficult to produce, but are more efficient and longer lasting. Polycrystalline solar panels are made from multiple silicon crystals. They are easier to make and produce very little waste, however they are less efficient. Passivated emitter and rear cell solar panels are similar to monocrystalline solar panels, however they reflect light back into the cell, making this new type of solar panel more efficient. Thin film solar panels are thinner panels that do not require frame backing, making them very useful for flexible applications. Looking at the impact solar panels have, we also want to consider the energy required to produce these solar panels with respect to the payback time. Each type of solar panel requires a different amount of initial energy to make, and they all have different efficiencies when it comes to generating electricity. The payback time for each type of PV panel is shown in the graph. The average payback time is 2 years, and after that, the rest of the energy is net positive.
The sun is Earth's most abundant form of energy. The sun produces beams of light, which is a stream of particles, those particles being photons. Photons carry the sun's energy as a massless particle that is absorbed by a solar cell. When photons reach a solar cell, they can refract off the cell or they can be absorbed. These photons are absorbed by the semiconductor silicon, which is used in roughly 95% of solar cells. Within the cell, there must be electrons free to move to produce a current. To do this, there is what is called a p-n junction, an interface between two types of semiconductor materials. To create the n-type semiconductor, or negative type, phosphorus atoms are injected into the silicon to create free electrons, which is typically a thin, heavily doped region. The phosphorus introduced an extra electron per impurity atom, which allows the electrons to become excited and move randomly when photons are absorbed. However, the random movement does not provide enough force to create a current. To establish this, boron can be injected into the silicon to create a p-type semiconductor, or positive type, which is typically a thick, lightly doped region. Introducing boron gives each atom a hole for an electron to move to. Now, when electrons are moving due to the absorbed photons, the electrons will move to the p-type semiconductor. This then makes a potential difference with a more positive type on one side and a negative type on the other. This difference introduces an electric field across a depletion region where there are no free electrons or holes, which makes enough force to create a driving current. The current that is formed needs to be able to become usable, which is done so through bus bars. Bus bars are the metal bars that are connected through copper wires from adjacent solar cells. The band gap of semiconductor materials plays a crucial role in the efficiency of solar cells. A material's band gap is defined as the energy needed to free an electron, or more specifically, the distance between the valence band of electrons and the conduction band. In metals, there is no band gap because the valence and conduction band overlap, as shown here. In a semiconductor, the band gap is small, and in an insulator, the band gap is very large. With too high of a band gap, photons may be unable to be absorbed into the cell and thus would not allow for the motion of electrons, resulting in no current. On the other hand, if the band gap is too low, the electrons will only need a small amount of energy to move. The extra energy from the photons will be transmitted to heat, which decreases the efficiency of the solar cell by 0.3 to 0.5% per degree Celsius above 25 degrees. Band gaps change among different semiconductors, with silicon at 1.1 electron volts, germanium at 0.67 electron volts, and gallium nitride at 2.25 electron volts. All photons do not have the same amount of energy, so choosing a material that allows for the most to be absorbed while also maintaining a low energy to not generate a lot of heat is best.
Applications. The day-to-day use of solar energy is becoming more and more prevalent every day. Already, the use of solar energy is widespread and appears in the vast majority of applications. As time continues, this technology will start to become a more universal power provider. From batteries and electricity to water and home heating systems, solar energy is responsible already for many homes' way of providing the essentials to their everyday life. This is accomplished using central and microinverters, which change the DC current provided from the solar panels into AC current, which enables the electricity made to become usable. The most efficient form of solar water heaters is known as an evacuated tube collector, which sits atop a solar panel. This is a very efficient form of water heating, as very little heat is lost during its path. In Tianjin, China, scientists and engineers are making strides. In Tianjin, China, scientists and engineers are making strides to incorporate photovoltaic technology into bus parking lots. A similar theory has been incorporated into car parking lots as well as roofs, but not yet for buses. It is estimated that it would be able to pay itself off within 4 years, as well as contribute greatly to net zero emissions and carbon neutrality. This method of providing essentially solar-powered public transportation would create a new aspect of photovoltaics. On the other end of the spectrum, solar cells can be seen at a very small level. In some places, such as large buildings, windows are coated in photovoltaic glazing, which consists of solar cells. As time goes on, more uses of solar cells will become more prevalent. More examples consist of use in calculators, becoming a more dominating force in the aeronautical industry, and even power electric fences and charging stations. Future of photovoltaics. Tandem solar cells have been the newest innovations. Tandem solar cells use two different materials which together are used to absorb more energy from the sun when compared to traditional solar panels. The two materials are silver and indium, which are required in much higher amount. However, these materials are more limited. Tandem solar cells use a specific design known as a silicon heterojunction. A heterojunction has two layers with dissimilar semiconductors which have unequal band gaps, unlike homojunctions. They are hybrid technologies that combine the best aspects of crystalline solar cells with thin film. Researchers have created tandem solar cells with 33.7% efficiency. This is incredibly efficient compared to average solar cells being about 17 to 22% efficient. Solar cell technology has improved vastly over the years, starting in 1957 with 1 to 5% efficiency, to now at 33.7. Huge leaps have been made in this industry. Solar cells will continue to grow as more research and development is put forward to find a solution to our energy crisis. These massive innovations shed light on what is to come from this amazing technology. So, with that being said, thank you guys for watching this guide on solar photovoltaics. Hopefully you found it useful and learned a thing or two. Be sure to leave a like, comment, and share. Thank you.